Hello everyone and welcome to our channel Mootechie. It's wonderful to have you back as we dive deeper into the fascinating world of dairy. Today we're continuing our exploration of dairy processing technology, focusing on two beloved products, cheese and yogurt. Get ready to learn about the science, the steps, and the different types that make these foods so unique and delicious. Now let's move on to our learning objectives for this lecture. By the end of this session, you should be able to discuss the science behind cheese processing, specifically the coagulation mechanisms, and identify different types of cheese with their respective processing steps. Explain the science behind the production of yogurt. And finally, differentiate between different types of yogurt, understanding their respective properties and how they are made. Coming up, we'll discuss our first major dairy product, cheese. Cheese processing is a captivating subject. Cheese is the most complex of the dairy products, involving intricate chemical, biochemical, and microbiological processes. The fundamental steps in all cheese making include milk acidification, milk coagulation, whey removal, and finally, packaging and storage. Let's understand this more clearly by looking at how cheese is classified. The type of cheese we get depends on several factors. These include the source of the milk, whether it's from a cow, a goat, or a buffalo, its moisture content, the composition of the milk itself, meaning its fat and casein content, the manner of coagulation, whether it's achieved through a change in pH or by using an enzyme like chymosin, the salt content and how the salting is done, and finally, the extent and condition of the ripening process. It's amazing to think that the International Dairy Federation lists more than 400 varieties of cheeses, like cheddar and mozzarella, each with a wide range of flavor profiles. Next, we explore the actual steps to produce cheese. At its heart, cheese is a concentrated form of two major milk components, milk protein, which is casein, and milk fat. The production begins with milk treatment, which involves pasteurization and standardization. Then comes the crucial step of coagulation or curdling. It's helpful to remember that milk protein consists of casein, which makes up about 80%, and whey proteins, which account for the remaining 20%. Let's now look at the mechanisms behind coagulation in more detail. This is the step where milk undergoes a profound physical and rheological change, a transformation known as gelation. Coagulation can occur in a few different ways, through enzyme action, acid addition, or a combination of acid and heat. The key factors that affect the aggregation of proteins are the casein concentration and the pH of the milk. First, let's talk about acidic coagulation. In fresh milk, kappa casein hairs on the surface of casein micelles cause them to repel each other, to bounce off one another. So coagulation is essentially the process of getting those casein micelles to stick together. How do we do that? A starter culture of bacteria is added to sour the milk. These amazing little bacteria convert lactose into lactic acid. This lactic acid acts as a natural preservative and also gives the cheese its initial flavor. Most importantly, the acid neutralizes the negative charge on the casein micelles, which allows them to clot together. What's really fascinating is that different species of lactic acid bacteria, or LAB, result in completely different types of products. The curdling time for this method can take anywhere from 2 to 16 hours, depending on a few things: the amount of inoculating agent added, which is typically 0.1 to 5% of the milk volume, the temperature, which is usually kept between 20 and 35 degrees Celsius, and of course, the specific type of starter culture used. Now let's look at the second method, enzymatic coagulation. This type of coagulation is accomplished by enzymes, which can come from animal, plant, or microbial sources. A common example is rennet. So how does it work? Imagine rennet enzymes acting like tiny razors that shave off those kappa casein hairs we just talked about. Without these hairs, the micelles lose their repulsion and can now stick together, aggregate, and form the solid backbone of the cheese structure. Rennet actually has two functions in cheese making. First, it causes the milk to coagulate. Since K-casein stabilizes the other caseins, its hydrolysis leads to the coagulation of the casein fraction. And secondly, during the later ripening stage, the rennet continues to work, breaking down milk proteins further, which helps develop the typical complex cheese taste we all love. Rennet is conveniently available in various forms, such as liquid, powder, and tablet. It's also interesting to note that for some soft cheeses, little to no rennet is used at all. Let us now look at the third method, acid and heat coagulation. This clever process permits the recovery of both caseins and whey proteins in a single step. The basic principle here is that whey proteins, which are normally stable in acid, become sensitive to acid coagulation after they've been heat treated. Examples of cheeses made this way include ricotta, mascarpone, and paneer. Here's the science. Whey proteins are denatured, meaning their structure is unraveled by heat. This exposes sticky portions of their structure. These sticky ends can then bond to each other or even bond to casein proteins, forming a solid curd. Before we move on, there's one more ingredient that plays a supporting role: calcium chloride. Cheesemakers often dilute calcium chloride or calcium chloride _2 in water and add it to the vat just before the rennet. So how does it help? Calcium chloride _2 aids the coagulation process in two main ways. First, when in solution, it forms calcium ions. Think of calcium as the glue that helps hold the protein structure together, making the curd firmer. Secondly, it can decrease the pH slightly, which in turn increases rennet activity and further promotes coagulation. Moving forward, we come to a critical stage: syneresis. Syneresis is the process of expelling the entrapped liquid, which is the whey, from the curd. This process is accelerated by cutting the coagulated milk into small cubes. The amount and extent of syneresis has a huge effect on the final moisture content of the cheese, which is obvious, and by extension, it dramatically influences the final texture and flavor. There are a few ways cheesemakers can encourage and accelerate syneresis: cutting the curd into smaller pieces, like with grana-style cheeses. This creates more surface area, allowing more whey to leak out. Cooking the curd. Heating the curd causes the protein structure to contract, literally squeezing out the whey. Stirring the curds and whey mixture. The motion and agitation can encourage whey expulsion. Pressing the curds. This is literally squeezing the sponge. Salting the curds, as salt draws out moisture. And finally, ongoing acidification, as the starter culture continues to produce acid, which also encourages syneresis. Following this, we have the stages of shaping and salting. In this step, the curd is shaped into its characteristic form and salted. The salt does two important jobs: it expels additional whey and it adds flavor. The salted curd is then placed or hooped into molds and pressed, often overnight. And this brings us to the final transformative stage: ripening. Ripening is the natural process of microbial, chemical, and biochemical reactions that occurs in a cheese after its manufacture and during storage. This is the magical step that gives different cheeses their unique flavors, textures, and appearances. Temperature and humidity are the two key factors that cheesemakers can carefully control during ripening to guide this process. The ripening of cheese primarily involves three biochemical processes: glycolysis, which deals with sugars; lipolysis, which deals with fats; and proteolysis, which deals with proteins. So to summarize the cheese production process, we have milk treatment, then coagulation, followed by syneresis, then shaping and salting, and finally ripening. Now that we understand the process, let's categorize the wonderful results. Let's look at the different types of cheese. First, depending on ripening characteristics, we have fresh cheeses. Fresh cheeses are easy to identify because they are typically white, shiny, and have no rind. They have the lowest fat content of all the cheese categories, usually around 19 to 21%. They also have the highest moisture content. Some delicious examples include halloumi, ricotta, feta, and mozzarella. In contrast, we have ripened cheeses. These cheeses are allowed to age and dry out in special rooms with controlled temperature and humidity. As they age, they lose moisture and shrink. The texture inside gradually changes from being moist and slightly crumbly to becoming dense, compact, flaky, and even brittle. They typically have a fat content of about 22 to 23%. Examples include Valenque and Clochette. We can also classify cheeses based on their moisture content. Let's start with soft white cheeses. These cheeses have a white crust that can sometimes be stained with reddish pigments or yellow-gray blotches of mold. They have a high moisture content, greater than 67%, which results in a fat content of about 24 to 26%. They are aged for less than 30 days. Examples include Brie de Melun, Capricorn Goat, and Charpam. Next, we have semi-soft cheeses. All semi-soft cheeses are washed in brine to discourage the growth of unwanted molds. They have a fat content ranging from 22 to 30%. They retain a lot of moisture, between 61 and 69%, because they are only lightly pressed. They are considered ripe from 3 weeks to 3 months. Examples are Taleggio, Langres, and Stinking Bishop. Then we have the hard cheeses. With these, the amount of whey expelled really determines the final texture. A simple rule applies: the more moisture removed, the longer the maturation can be, and the more complex the final flavors become. They are considered ripe from a few weeks old, all the way up to 3 years. They have a fat content of 28 to 34% and a moisture content between 49 and 56%. Classic examples include Manchego, Emmentaler, and of course cheddar cheese. And finally, we have flavor-added cheeses. These are hard or semi-soft cheeses that are combined with other ingredients like fruit, spices, garlic, nuts and herbs. Examples include nagelkas and idiazabal. So to summarize our section on cheese, this chart nicely illustrates the entire production journey from milk to the final ripened cheese. Now let's shift our focus to our second main topic, yogurt production. Yogurt is produced by the controlled fermentation of milk by two specific species of bacteria, Lactobacillus species and Streptococcus species. For a satisfactory, well-balanced flavor to develop, it's important to have approximately equal numbers of both species present. This is because they have a stimulating effect on each other's growth, a wonderful partnership. The volatile compounds produced by these yogurt bacteria include small amounts of acetic acid, diacetyl, and most importantly acetaldehyde, which gives yogurt its characteristic tangy aroma. Let's break down the teamwork between the bacteria. Streptococcus thermophilus is the pioneer. It gets things started by bringing the pH of the milk down to about 5.5. Then Lactobacillus bulgaricus takes over, vigorously converting lactose into lactic acid. Additionally, proteolytic enzymes from L. bulgaricus break down milk proteins into peptides. The lactic acid produced is what ultimately coagulates the remaining milk proteins, causing the yogurt to thicken into the gel we know and love. Let's understand this more clearly with the basic science of yogurt. Chemically, the transformation of milk into yogurt is a change from an emulsion to a colloid. An emulsion is a mixture of two liquids that don't normally mix like oil and water, and milk is an emulsion of water and milk fat. A colloid, on the other hand, is a dispersion of solid particles in a liquid. The predominant protein in milk is casein. In raw milk, casein forms structures called micelles. As the bacteria grow, they produce acid. This acid, which lowers the pH, breaks up the micelles. The casein proteins then come together to form a three-dimensional net that traps water and fat, creating the solid yet soft structure of yogurt. Now let's explore the different types of yogurt you might encounter. First, there is set yogurt. This type is incubated and cooled in its final package. It forms a solid set or curd, where the yogurt firms up in a container and is not disturbed, resulting in a firmer texture. Then we have stirred yogurt. This yogurt is incubated in a large tank. After incubation, the coagulum is broken by stirring before it is cooled and packed. This gives it a less firm texture, more like a thick, creamy custard. And finally, there is drinkable yogurt. This is similar to stirred yogurt, but with additional milk and flavors mixed in to create a beverage consistency. To wrap up, this slide outlines the key production steps for creating yogurt, taking us from milk preparation all the way to packaging. Thank you for joining this deep dive into cheese and yogurt processing. We hope you enjoyed learning about the science behind your favorite dairy foods. Thank you. See you in the next class.